Hi, welcome to today's video on Introduction to Natural Language Processing. My name is Vishal Vadina. I'm the lead of Applied Research Unit at Quantiphi, where we explore cutting-edge areas of AI research with a specialized focus on their translation to real-world applications. We cover a broad spectrum of research areas and a variety of industrial applications, and from time to time, we share our accomplishments, point of views, tutorials, as well as our mistakes and learnings from them to the data science and research community here. In order for you to understand and appreciate the upcoming content in NLP, I would like to set a base with today's session on Introduction to NLP, where I wouldn't go into too much of the technical details, rather focus on the journey of how the modern day NLP techniques have evolved over the years, how it started, the breakthroughs, and where it stands now. So if you're a novice and getting started in NLP or just want to understand the NLP landscape better, this video might help you a lot. We're also adding a blog on the journey through natural language processing and natural language understanding that might cover a few more details. So if you're already an NLP expert and are familiar with the concepts being talked about, feel free to check out the blog in the description. There are a lot of resources and references pointed out to get more out of this video, so make sure to check out the blog as well as the rest of the videos as well. The upcoming content and videos would slightly be in the healthcare and life sciences context, so you'd find some of the examples mentioned in this video referring to the biomedical space. Having said that, let's start. So natural language processing deals with natural language, that is the language that evolved through human usage, right? This is different from the machine language or the programming language, and as the name suggests, NLP is the processing of this language, which deals with three fundamental steps, right? The analysis, the derivation, and the understanding of the information, right? So if you look at any major area of NLP research right now, they focus on at least one or more of these three fundamental steps, right? So we have data and linguistic analysis for the analysis part, we have information retrieval, also called as IR, for the derivation part, and we have NLU, which is like natural language understanding, for understanding the derived information, right? So in the earlier days, a given piece of textual information is like broken down into multiple levels, as can be seen in this figure here. So given a sentence, you have like a bunch of characters and you bring together a bunch of characters, you find a word, and then you add a couple of letters to this word. Again, it becomes a new word. Like in this example, Alice talked to Bob. You add ed to talk, and it's just a past tense of talk, right? And then you have a lexical analysis, and then you have syntactic analysis, where you bring in the parts of speech, like this is a noun, this is a pronoun, this is a verb, etc. And of course, like you have semantic and discourse analysis, where like you find out that there is an agent called Alice, and then there is an agent called Bob, and then Alice talked to Bob, which means there was a communication event that happened together, right? So this was how we humans understand a given piece of a text, without even making a conscious effort for a second, right? But computers couldn't understand these references to lexical and syntactical relations as we humans did, right? So there was a need to dissect this information in a way that machines could understand, and as we all know, machines only operate on numbers and math, right? So we had to find a way to represent this information in a numerical way, and it led to something called as representation learning in NLP, right? So people started initially with one-hot encodings, where every word is represented by a vector, with ones, and the rest all are zero, right? And the length of this vector would be equal to the vocabulary size, which is as many words there are in the given corpus that we're dealing with, right? So naturally, we can see the drawback of attaching your vector size to the vocabulary length, because it becomes very hard to represent larger corpuses where we can even have like millions of words. Plus, these vectors look very sparse with very limited information, because most of the times, about 99% of the time, they're just filled with zeros, right? So we then move to the bag of words approach, where in a given example, like when we have two sentences, Mary is hungry for apples, John is happy he's not hungry for apples, right? So here each word is scored with respect to the number of times it occurs in a sentence, right? So each word is now represented by the vectors of integers, taking the entire column as a vector, right? And this was also not ideal, since here too there was plenty of sparsity. As the vocabulary increases, you'd see a lot of zeros, and you can only observe a handful of words in a given sentence at any given time, right? So also the words here are given a similar weightage, like in this current example, the words like hungry and the words like ease are probably at a, like they're given the same weightage, but when you consider these two words, they're probably at a different level of interest for the end user, right? So this doesn't consider the different weightages, and also this doesn't consider the order of words as well, which carries a lot of information. Like in the example we saw earlier, Alice talked to Bob versus Bob talked to Alice. They're two completely different sentences, but if we use that, we would get very similar looking embeddings, like the exact same embeddings in both the cases, which is not ideal, right? The numbers that we see here are called term frequency, since it's the frequency count of each word in the given sentence. The researchers then updated this to TF-IDF, which is term frequency inverse document frequency, where these term frequencies in concept are divided by the total number of times these words occur in the entire document. So this solves the weightage issue. So now the words like the, is, etc. are now scored a lot less compared to something like Mary or hungry, for example, right? So this solves the weightage issue, but this doesn't solve the order of the words, which is like a bigger issue, right? All in all, these initial methods use ones and zeros and counts and other statistical methods that are like pretty limited. These this also made it very difficult to use these vectors in algebraic operations that proved to be a lot more useful. So this led to our next method of representations called embeddings. So far, all the techniques we've seen include constructing these word vectors manually, either by taking frequencies or by other methods. So with more and more algorithms coming in, it proved essential to let the machines learn these vectors themselves rather than manually present them with the vectors, right? So these learned vectors of representation are called embeddings, and these play a very crucial role in NLP, right? And it wouldn't be an exaggeration to call embeddings kind of like the heart of NLP, right? So instead of ones and zeros, we now have an n-dimensional vector that's represented by floating point values that can range from negative to positive, usually within a specific range depending on how we derive these vectors. But the main difference is that these are self-learned by the machines and these are not manually notated, right? And this has obviously a lot of benefits. Firstly, because these are machine learned, so we can tune the machines to learn different representations depending on the needs, right? And this can be very less dimension and fixed irrespective of the vocabulary size. So it doesn't matter if we have 100 words in our vocabulary or 100 million words in our vocabulary, the size of the dimensions could still be the fixed, right? And again, these representations are also much more dense compared to our previous approaches where everything is like filled with zeros 99% of the times. So because these are dense, it's much more easy to work with these for matrix multiplications or other algebraic operations on top of them. But the biggest advantage of all comes with the semantic learning of the word, which we'll see soon, right? So okay, embeddings are a much better way of word representations, and these are learned automatically by the machine themselves. Great, but how? We have a few techniques, right? Word2Vec is a technique that explored the usage of neural networks for learning the word representations automatically, and this was released back in 2012 by Thomas Michelov and others. So this has two methods, CBOW, which stands for continuous bag of words, and skipgram. These are two identical techniques but are exactly the opposite approaches, right? So the bag of words approach looks at a particular context. In this case, the context is two words, right? For example, if you have a current word, you look to two words to the left and two words to the right. So you look at that context and you try to predict the given word. In this case, yesterday was and beautiful day is a given context, and we had to predict really, right? And the skipgram technique is pretty similar, but it does the opposite, where for every given word it tries to predict the context. So in this case, when we have a word really, it tries to predict two words to the left like yesterday was and two words to the right, beautiful day, right? And the learned representations in the hidden layers of these neural networks are our actual word embeddings, right? So Obviously, this had a lot of benefits, but one of the most interesting observations from these learned representations was the similar distance between words with similar relations, right? So in this case, like again, this was taken from that same original paper. It was interestingly observed that man and woman, or male or female, had similar distance between them as king and queen, for example, right? And even in the case of like country and capital, for example, like China and Beijing had similar distance between them as Japan and Tokyo, right? And remember, these embeddings are not trained to be in such a way, right? These are self-learned, and that's a pretty interesting observation, and this has led us to apply a lot of algebraic operations on top of these embeddings. So we could even mine some rules, like for example, if we know that the association of a man is to a woman and we need to find the similar association to a king, then all we had to do is king minus man plus woman, and we would end up in a space that's pretty much closer to queen, right? So again, this was a pretty interesting observation and a pretty interesting step forward, because this allowed us to use a lot of algebraic operations which a lot of earlier techniques couldn't do. So this was a great benefit, but of course this also had its own limitations, right? So this only had like a very short context. You could only look at n number of words to the left and to the right. So, and it was a fixed size. It wasn't dynamic, it wasn't machine learned, it's a tunable parameter. We, like, the end user has to specify and tune that parameter, right? And we still are unable to learn multiple co-occurrences of the target context word. So this doesn't take the global co-occurrences into consideration. So if there is a word that occurs at the beginning of the document and then at the end of the document, this algorithm would probably not know that, okay, these two are the same words that are occurring in two different contexts, right? And one of the main drawbacks is that it only gives one embedding for a given word. So these are not contextual, and we'll look about them in the upcoming slides. We then move on to GLOVE embeddings, which stands for global vector representations. So this doesn't do anything significantly different. It just uses the global co-occurrence matrix, which keeps track of how many times a word comes in context with other words globally, right? So the learned representations is then multiplied by this matrix so that the words that frequently occur together globally have higher scores compared to the others. So this, as we can see, outperforms word-to-vector representations, both the CPERV and both the skipgram methods, and it outperforms in multiple downstream tasks, right? But this still has its own limitations, where the previous limitation where we only have one embedding per word. So in this example, which says like he went to the prison cell with his cell phone to extract blood cell samples from inmates, right? So every instance of the word cell here has a different meaning to it, right? But if we use these word embedding techniques, you would only get like one embedding for this word, which is not ideal, which doesn't capture all the information that we want, right? So now we have a set of word embeddings, but what do we do with them, or how do we use them, right? So this depends on our downstream task and our choice of how we compose these embeddings together. So in this example, let's take a downstream task example of text classification, right? So you have an input called itching in the eye, and it goes through the text classification module, and we give the output as something like conjunctivitis, right? Which is an output prediction of a class, right? So how this prediction happens is, we send this input itching in the eye to the text classification module, and inside that module you would generate a low dimensional composite representation of the entire input sequence, on top of which we add a softmax layer, which often converts that into a probability distribution over our entire target classes. And in this case, it's probably the list of all the diseases in our vocabulary, right? And as we can see, like here, conjunctivitis has the most probability, so that was given as the output, but also the similar diseases to conjunctivitis like uveitis or something like that has next higher probability, right? So the composition of these embeddings decides how we go from a bunch of words or their individual word embeddings to a composite low dimensional representation of the entire input sequence. And a couple of common techniques used earlier were something like concatenation or even addition, right? So in this case, like etching inside the eye, you have like one word embedding for each word. So in this case, like for 4 tokens, we had 4 different embeddings. So all of them are, for example, concatenated together and are like sent into a neural network module, which then kind of composites all of them into a smaller dimensional representation, on top of which we apply the softmax and make these predictions. And similar to concatenation, we could even do addition, where you just add up all these individual word embeddings, and the rest of the process continues, right? So these had a lot of benefits, like this removes the sparsity problem, and the model size is also not exponential. So these were like pretty fast, but they come with their own limitations, right? Because you still need a fixed window size, like especially with concatenation. If you like look at 2 words to the left and 2 words to the right during the training phase, and you want during the inference to look at 3 words to the context, it won't work that way. The context window size still needs to be the same, and this doesn't take into account the word order, right? And especially for addition, like even if it is itching inside the eye or something like eye inside the itching, which absolutely makes no sense, you would still have the same composite embedding, because we're just adding it together and sending it to the network module, and you would still end up with conjunctivitis probably, right? But it shouldn't, right? Because that doesn't make sense, right? So there are a lot of other techniques to compose these embeddings as well, element-wise operations, like concatenations, and some are in a couple of examples that we've already seen. But eventually we've moved to parametric techniques like RNNs, encoder-decoder frameworks, etc., which we'll see going forward, right? So RNNs are a family of networks that is used for, or rather I would say well suited for, sequential tasks due to its nature of what we call as unfolding, right? So what we see on the left here is a folded RNN, and then when it unfolds, it kind of looks like how it looks on the right hand side. So in this case, it has 4 steps. So each step is in the unfolding is called a time step, and in this particular RNN cell has 4 time steps because we have 4 input tokens itching inside the eye, right? There are a lot of variants of RNNs as well, LSTMs, GRU, bidirectional LSTMs, etc. But depending on what variant we use, the output kind of differs, and we'll cover a little bit into the details of what those variants mean. But when you look at an unfolded RNN cell, you see that it has 2 outputs, right? So one that goes to the top and one that goes to the right, right? So as I said, like depending on the variant that we use, these outputs might be the same or might be different, but the concept technically remains the same, right? So the concept here is that at the current time step, when you look at the current input token itching, it does some processing inside this cell, and then it sends that output to the right time step, right? So in the second time step, you now have 2 inputs, one that comes at that particular input token, which is the input token is inside, as well as one that comes from the previous time step, which is the processing on top of itching, right? And this does some processing and then passes the information towards the right time step, which is the 3rd time step, right? And then this passes it to the 4th time step. So the intuition behind this is when you come to the final time step, you have 2 inputs, one from the current input time step, and also the vector that comes from the previous time step, which conceptually has all the information that has occurred in the network so far, right? So the final output that comes at the final stage encodes all the information of the entire sequence of inputs. That's the theoretical intuition behind an RNN cell, right? So, and thus we can see how this would be like pretty great application for a sequential task, something like in natural language processing, where you have dynamic length of inputs coming in, right? And in this nature of unfolded RNN, we see that the information is being passed to the right. So this is like left to right RNN, but we can also have another layer of RNN that goes from left right to left, and then concatenate each other, which then makes it a bidirectional RNN. And the bidirectional variant of the LSTM is also called as bidirectional LSTM, right? So these are, again, a couple of techniques that would be used for a lot of composition of these embeddings that would be used in machine learning approaches. And they obviously have a lot of benefits. The model size here doesn't increase for longer inputs, because this has like a weight sharing mechanism. So even if we have 4 tokens, or even if we have 40 tokens, even if I input the entire passage, the layer parameters would still be the same. And this in a way solves the order of the words problem, right? So now we have like a particular order to the given sequence. So this helps in understanding the order of the given input as well, right? But this also has its own limitations, where it's pretty time taking for the RNN computations, right? And it's pretty difficult to access the information from the previous time step, where this is fairly known as the long-term dependency problems in RNNs, due to the vanishing gradient issues that this faces. We often see that the information that is output at the final time step is heavily influenced by the last few time steps compared to the time steps that are probably 20-30 different time steps ago, right? So this was a problem, that it couldn't look at the information, or couldn't attend to the information at the beginning of the sentence as much as it does to the very recent portions of the time steps, right? We then move to, like after the success of the RNNs and LSTMs, of course, they are like used in a unique combination, which led to this encoder-decoder framework, right? So, like the way it works is like you give an input sentence to an encoder, which is mostly an RNN or an LSTM in this case. It encodes that information, and you pass that to a decoder, which kind of decodes that information and generates the output tokens, right? So in this top example, you have the Russian translation, or like Russian input sentence of that contains words like "I saw cat on mat," which goes to the encoder, and the encoded portion is moved to decoder, which translates to English like "I saw a cat on mat," right? So this is how the translation systems regularly work. And you could see how it works. Like each word will be represented by its own token, and all of them go into an individual time step of that particular encoder network, and the final encoded portion goes to the decoder, which then again, like the output goes to the next decoder time step, etc., which helps in generating these output sequences, right? So this had a lot of benefits. So since the introduction of this framework, this has become so popular that almost all the sequential problems in NLP uses this encoder-decoder paradigm, even to this day, right? And there are like a wide variety of such problems and settings where this can be used, especially in NLP, right? So there are different types of sequential problems that we come across in machine learning often, right? So it starts with one-to-one, which like a typical example is image classification, where you have like a fixed size of input and a fixed size of output, right? There's no sequential information here. And then there's one-to-many or many-to-one. Like for example, one-to-many is something like a image captioning, where you have like a fixed size input, but depending on what's in that input, the output size might vary, right? So like an example of image captioning is like when you look at an image and the output says a man in the black shirt sitting on a stage with a guitar, for example. So it just describes that image, right? And then many-to-one is kind of opposite of one-to-many, where it's similar to the example that we've seen before, like itching inside the eye. Right? So something like a text classification where you have multiple input tokens, and the output is always fixed. It's just like one of the classes in your vocabulary, right? So that's many-to-one. And then there are different formats of many-to-many. Machine translation example that we've seen in the encoder-decoder slide is like a good example, where you have a dynamic sequence of inputs that goes in to the encoder and a dynamic sequence of output that comes out of the decoder, right? And another form of many-to-many is for example, token classification, and in this case something like entity recognition or parts of speech tagging, for example, are a couple of examples in NLP where the encoder-decoder frameworks can be used, right? So they're used in almost all of these scenarios. And the development of such encoder-decoder frameworks, or the popularity of those frameworks, have now given an opportunity to learn contextualized vectors or contextualized embeddings, right? And the ELMO is one of the first instances which used bidirectional LSTMs in an encoder-decoder framework to learn a language model and then obtain the embeddings from it. ELMO stands for Embeddings from Language Models. Okay, like there are like a couple of new introduction, like new tokens or new words that are introduced, right? So what is a language model? A language model is a model that understands the corpus such that it predicts the next word given a context of words, be it the next word prediction from a group of words, or a middle word from a given sentence, or even the next sentence altogether given a group of sentences, right? So ELMO builds a bidirectional language model, since it uses bidirectional LSTMs and can see both left to right and then right to left. So it can look at the left side of the context of the current word and the right side of the context of the current word as well, and then generate the contextual embeddings. So it leads to, what it leads to is, in this given example, I read a book every day versus I read a book yesterday. In both these cases, the word READ have different embeddings because they carry different meanings depending on the context, right? So in this case, that embedding mostly depends on the part that occurs to the right, which is it's every day versus yesterday, right? So obviously this has a lot of benefits. The word embeddings are now contextualized, which means for a given single word you can have different embeddings depending on the context, and this has paved a lot of benefits in transfer learning, right? And as I said, like this has been like a game changer in NLP research, where understanding the context is generally considered as a much better understanding of the given corpus, right? So while these contextual embeddings are being developed, there was another invention in parallel that helped in the performance of these encoder-decoder frameworks, trying to improve upon the drawbacks that we see. And even in ELMO, we see a drawback, which is it still uses the LSTMs or RNNs, for example, so it's pretty slow to train, but this still has the same old drawback of the LSTM, where you have these long-term dependencies, like so as long as you use LSTMs and RNNs, right? So the next concept is attention mechanism, which kind of tries to improve upon it, right? And this is a breakthrough innovation where it allows the decoder to take a peek at all the observable input states while decoding, right? So in the figure, if you could see, while predicting the target at the current time step, it now can look at not just the input that comes from the previous time step, but also can look at all the individual input encodings and then decide what the end output would be, right? So how it translates to in our example is, for predicting conjunctivitis, it can now look at all the input tokens again, like all the embeddings of the input tokens again, like itching inside the eye, and it can learn what input encoding to attend to the most while making the prediction. So in this case, the word eye would probably have like a lot of meaning or a lot of weightage in order to give the output as conjunctivitis, right? So if it was itching inside the ear or something like that, conjunctivitis would be probably nowhere close, right? It would be some other disease, for example, right? So all the small a's that you see here are the attention weights, which the model kind of learns itself. So if I have to predict this as conjunctivitis, then okay, I is the one that I need to focus on. So this is the kind of mechanism that allows this decoder to take a peek at all of these input encodings and actually learn, the model would learn itself on where to give like more attention, right? So as I said, this has been like a breakthrough innovation, and this has a lot of benefits now because it kind of solves the long-term dependency issues, because now the decoder can peek at all the input tokens and decide which one to focus more on, rather than being heavily influenced by the recent input tokens, right? But this does also have a drawback, where this is a unidirectional, which means it only looks at the tokens that have already occurred, right? So if the example were itching inside the eye only during the shower, for example, conjunctivitis is nowhere near to what the sentence means. But at this given input token, at this particular eye token, like it only looks at the ones that has already existed. So for that particular decoder step, it only gives conjunctivitis as your output, but it's still unidirectional, which is kind of a limitation for attention, right? So while attention has improved a lot of performance on a lot of downstream tasks, it has paved the way for better innovations, leading to frameworks like transformers, right? So now we're in the area of talking about scale, about volume, about improving the state of the art by over 20%, which is unimaginable in general cases, right? But all of those have been possible due to transformers being at the forefront of it, right? So this is also a typical encoder-decoder architecture, but this comes with a lot of innovations internally, especially something called as self-attention, right? So this improves upon the previous attention mechanism, which could only focus on the left part of the context, if you remember. As in the self-attention, the word could look at the entire sentence, including itself, and hence it's called self-attention, right? So because there's self-attention, when you're picking at every input word or token, this removed the need for recurrent networks, because you don't need the order anymore, or you don't need the like the sequential nature anymore, because now you're just picking at all the input tokens, right? So no RNNs or LSTMs in the entire transformer network, right? And the entire learning is only possible due to self-attention, right? This also includes positional encodings, because now that we don't have any RNNs or LSTMs going from one direction to another, we lose the sense of direction and word positional information, right? So these positional encodings provide this extra information, so the model could learn the typical positions and the order of the tokens as well, right? So again, this paper introduced a lot of new concepts that it would take at least 30 to 45 minutes to just go through this in detail, and there are a lot of videos that do a great job as well. So I won't go into the much technical details of what multi-headed attention is, or what the residual connections or the linear layer does here, except I would jump into the technical highlights, where I could say that this has been one of the landmark moments in NLP research, and has brought in a wave of pre-trained models in this space ever since this was released in 2017 by Google Research, right? It has been so famous that there are a lot of state-of-the-art networks that came after, that even only focused on single portions of these transformers, like only just transformer encoder or only just transformer decoder, right? So GPT is a good example of a network. GPT stands for Generative Pre-training from OpenAI. This is a good example which only uses the decoder part of the transformer network, and it can be used to solve like multiple downstream tasks like classification, entailment, multiple choice question answering, machine comprehension, etc. Right? This does have like a minor drawback, because it uses only the decoder part of the transformer. It is a unidirectional one. It can't look at the future tokens, right? And the next example, which is BERT, stands for bidirectional encoder representations from transformers, is another example which only uses the encoder part of the transformer, right? So again, probably a lot of you folks have already heard about BERT. Needless to mention, this has become pretty famous in the NLP community, revolutionizing the the transfer learning paradigm so much that there are currently more than around 50 different variants of BERT, since it is very easy to fine tune to a custom domain or to a custom downstream task. right? And this pretty much uses the same concepts of self-attention and positional encodings from the transformer, because technically this just uses the encoder part portion of the transformer, but this does it with one minor change, right? And that is masked language model that BERT introduces, right? So in a given input sequence, the tokens are randomly masked, and the model is trained to predict the mask looking at the context around the token. So in this case, when you have an example like diabetes is a common disease, its symptoms are etc., etc. Let's say like a given token, for example, disease is randomly masked, and then now the model has to look at the context, like diabetes is common mask, its symptoms are etc. So it has to predict that that mask token is actually disease, right? So as you can see, this is an unsupervised setting. There are no labels, there are no handmade annotations like that are required. So thus it was like very easy to fine tune it to a custom domain, or like given a custom data set, or even custom downstream tasks, right? And it has been designed to take multiple sequences as well, so it can be easily used for a lot of downstream tasks without many changes. And a few examples of these downstream tasks are, for example, like giving a synonym score, like when you have like a similarity score between two given passages, be it sentences or like multiple sentence passages. So you can have sentence 1 like head spinning a little, and then sentence 2 you have dizziness, which probably is like pretty much same. So you can pass these two sequences like separated by a SAP, which is a separator token, and the model would just output a numeric score like something like 0.93, which tells that how similar the given input sequences are, right? And another example is text classification or single sentence classification, for example, like we've seen before. So this is just to show that like you need not have multiple sentences all the time. You can even have like a single sequence or a very lengthy passage as well, and it can still take that as an input. In this case, the patient has cough, fever, and night sweats. If this is like the given input sentence, it can probably be used to predict the outcome class is something like pulmonary tuberculosis, right? So another example is model comprehension, which is another name for question answering, where you just give two inputs. One is a passage or question, and the other is a passage or the context of where this question can be answered from. So if there is a paragraph that says like TB infection happens in 4 stages, and these 4 stages happen over roughly over a month, and the question is how many stages the tuberculosis have, you just have input both these input sequences together, again separated by a separator token, and we can tune this model to give the output as the start and end token of the answer. So in this case, the start and end token is 5,6, which means the answer starts at the 5th token in the passage and ends at the in the 6th token. So when we translate that from the given paragraph, we get the answer as 4 stages, for example, right? And then we can also use it for individual token representations, where we can have something like entity recognition, where you have a given sentence and you have a few tokens of interest in your given sentence. We can even tune this model to highlight that every word that is an entity. It can give like an entity score for each and every word, which will allow us to pick up the entities of interest in a given sentence, right? So as you can see, with multiple downstream tasks now made possible and easy without much manual intervention in the data sets, BERT has paved a way to develop multiple domain-specific variants, as well as developing very large-scale language models using tons of data, right? So, as I said, like in case of like domain-specific language models, we have something like Clinical BERT, which is from MIT and Microsoft, which includes more than 2 million admission and discharge nodes, right? And it has been tuned. It's a variant of BERT that has been tuned using like medical clinical nodes, and that's the reason it's called like Clinical BERT. And it has around 110 million parameters in it, right? And then we could also see Biomegatron, which is from NVIDIA, which has around 4.5 billion words, right? And in terms of parameters, it's almost like 10 times, more than 10 times more. The larger version of the Biomegatron has around 1.2 billion parameters, where this entire data set has been fine-tuned on PubMed extracts, right? So these are all like fine-tuning the masked language model of BERT on top of custom datasets, right? After Biomegatron, we could also see the Getter-tron, which is again from NVIDIA in collaboration with University of Florida. This was fine-tuned on 10 years worth of EHR and Wikipedia data, and it has around 90 billion words in its corpus, right? And the parameters also increased to around 3.9 billion parameters, right? And not a custom language or a domain-specific language model, but a generic one is also like a GPT-3, which probably a lot of people might have heard from OpenAI, which has around a mammoth 499 billion tokens of text data, right? And this has been like a generic language model that has been trained from multiple data sources from the internet, and this has around 175 billion parameters, right? And this GPT-3 is not the largest model currently in terms of parameters or even the number of tokens used, right? So recently this year, Google has released a Switch Transformer, which whose large version has around, and I'm not kidding, 1.6 trillion parameters, right? And to compare with clinical BERT, which has around 110 million parameters, it's about 1.45 million times more parameters. It's just crazy. And what's even crazier is that all of this surge happened in just less than 2 years. Within just last 2 years, we've seen a massive surge in the amount of data set that is being thrown at these algorithms, and the humongous surge in the model parameters and the mammoth size of the language models as a whole. Right? And clearly this isn't the end. Pretty sure someone must be developing 100 trillion parameters model at the back end. It's just crazy all over. But craziness like this has what made natural language understanding possible to the level it currently stands at today. So there are only brighter things going ahead, pushing the boundaries forever, and hence there's a great need to understand these latest developments and to actually make use of these developments in real world applications for the benefit of all of us, right? So with that, I would like to conclude this session. There's a blog attached in the description that covers the above concepts and more in a slightly more detailed fashion, with a bunch of resources and references at the end for you to explore and learn more about. So make sure to check that out. And I also want to give a huge shout out to the NVIDIA Alliance team at Quantiphi for putting together this beautiful looking slides. And yeah, if you have any queries, concerns, or feedback, please reach out to us at appliedresearchmedia@quantiphi.com. And please stay tuned to this space for more informative videos and sessions. I assure you we have some pretty interesting stuff coming soon. Thank you, and I'll see you in the next video.